Alrighty, this is homework 2. So in this question, we didn't have a worksheet we were working off of, so I just went ahead and put it in here to refer to. A driver is to test the braking distance of a car equipped with anti-lock brakes, which can decelerate the car at the maximum possible rate without the tires skidding. The test is made on a dry, straight section of a track. In response to a visual signal, the driver stops the car in the shortest possible distance. Stopping distances for 6 initial speeds are given in the following table. Find an expression for the stopping distance d in terms of the initial speed v, the response time t of the driver to the visual signal, and the magnitude a, which is constant, of the car's deceleration. Alright, so in addition to looking for or coming up with a formula, we're also looking for, of course, acceleration and t, because otherwise we would just have a formula with unknown variables. Alright, so moving on. So what I've got here is I've just got a few general equations because I'm plugging really everything into Excel, but most importantly, our distance equation is really just equation 2, but and that comes from, we know, a velocity with respect to time equals initial velocity plus acceleration times time. You integrate that, then you have this nice formula here, which is delta x equals initial velocity times times plus 1/2 acceleration multiplied by t squared. However, we can't do much with this at the moment as we don't have time or acceleration. Now we know time is the independent variable here, so if we were to just graph it, we would just need acceleration. However, we're looking for both a and t in all of these equations. So in order to find a, I went ahead and jumped down to I believe it's equation 3, which states velocity squared equals initial velocity squared plus 2 times a times the difference of x minus initial x, but of course that's final position minus initial position. And if you do a little bit of algebra on this problem, you'll end up with this nice equation over here stating acceleration equals velocity squared minus initial velocity squared divided by 2 times delta x. And for all of these, every time this is used, it's going to give us a negative acceleration, which is important to note. However, in the next page, our acceleration does show up as positive because we're just looking for, the problem states that we're looking for the magnitude of acceleration. And then once we have a, it's really easy to find t. We're just able to look at our velocity with respect to time equation because we have all the other variables. We just take velocity, subtract initial velocity, and divide by a. We have that over here, and we get time. Let's see, and so here I just took all of our measurements, lined them up side by side, and I calculated them. So here we're calculating, as we spoke, the magnitude of acceleration, which is, in our case, it's truly just, we know that final velocity is 0, and initial velocity is just these numbers here on the left. So velocity squared divided by 2. Now typically, this would be negative. However, once again, we're taking the magnitude here, which over here in our seconds calculation, these values are still negative, which is important to know. Otherwise, if we were to calculate with the magnitude, we would come up with negative seconds, which of course would not make sense. So yeah, we're able to do this because we know our initial velocity, which is given, and then our final velocity, which is implied since we're braking, is we just know it's 0. So here's our acceleration here, and then our seconds. and as you can see, acceleration does increase, or it's higher for the higher values, that is a larger distance traveled and higher velocity. Then in addition to that, our time is going up at a pretty consistent rate. Here it's showing as just about 0.6, might be like 0.55. Just pretty interesting. So there you go. Hope you enjoyed.